A cylindrical capacitor has radii A equals 0.19 centimeters and B equals 0.23 centimeters, as in the figure. Find the radius r such that the fraction of the total energy that is within a cylinder of radius r is 0.27. So we've got our inner radius A and our outer radius B, and we know that the only thing that matters for B is the distance to the inner part of this cylindrical conductor, because that's where the charge is going to live, so that's where we're going to draw our potentials and so on. And then we're going to say find some smaller cylinder, some region here, such that the energy within this region is this number, this fraction of the total energy in the capacitor. So that's our goal moving forward. I don't really love these pictures, so I'm going to switch to a new page and draw my own picture with my own couple symbols and stuff on it for us to look at. So let's go to the next page. All right, so here's our redrawn cylindrical capacitor with our two little coaxial conductors. And I'm going to do a little bit of a cheat, or at least a redefinition, and I'm going to ignore their definition of little r for the moment, because I need a radius, and they've used up the one I want. So don't worry about it, but I'm going to say what I'd like to do is find out what energy is contained inside a cylindrical shell whose radius is r, and whose thickness, actually I guess we should do this solid, so radius r and thickness, and here's where my art skills kind of fail us, but here we go. This region, now this is not a conductor or anything, this is just a mental region of this cylindrical shell, like that, whose thickness is dr. And I'd like to find out the energy that's inside that shell, and of course theoretically all this little bit too. And I'm going to start with the idea that the energy in that infinitesimal little shell would of course itself be infinitesimal, and that would have to be the energy density, oops, I don't have a good, let's say that energy density times the volume of that little shell. So some dV of volume. And we're going to want to get that energy, and then the energy in the whole region from the origin out to here, which really would start from the inner shell out to here, the whole green shell, or the whole green region, not just the cylindrical shell. That energy would be just the summation, the integral, of course, of all the little energies. And then we'll see how we want that fraction, that to be some fraction of the total energy. Let's get the volume element first. The volume element dV is going to be this circumference times this thickness times the length that we use here. It's going to be the area of the shell times the length of the shell. And so that's going to end up being 2 pi r dr times L, where L is our unspecified length of the cylinder. And you're going to see it doesn't really matter what L is, but there you go. It's our length of the cylinder. And I'm going to remember that, and I want to make a note so I never forget, this is a volume. We've got too many letters in here, like U's and small u's and v's and so on. This little curly v is meant to be the volume, not the voltage. We won't be using voltage directly in this solution. But we do say that, well, we've got an electric field coming around, obviously, from the inner and outer shells. We could do, we could do a Gaussian surface, and we could say E dot dA through our thing is going to be something like the enclosed charge. In fact, it's going to be the enclosed charge over epsilon. And this is going to be E times an area E dot dA is going to be just EdA. E is going to be constant because we're at a fixed radius, and so we're just going to integral dA over here. And the enclosed charge, of course, is going to be the charge density lambda times this L over epsilon. But of course, integral of dA is just going to be 2 pi r times that L is lambda L over epsilon. So the electric field is lambda over 2 pi epsilon naught 1 over r. And to be honest, I don't care about any of that except this bit. So I'm going to write the electric field as some constant over r. But then the energy density, little u, is always 1/2 epsilon naught E squared. So that's going to be 1/2 epsilon naught C squared over R squared, which I'm going to represent as 1/2, or actually I'm going to just represent as some other constant C star over R squared. The key thing is that these constants, the C, little c's here, C and C star and so on, they're all geometric factors. They don't depend on anything. They don't change from one to the other. The only thing that's changing here is the radius we're considering. So the length of the conductor, the charge on the conductor, all of that stuff doesn't change. So I'm just going to abstract it back into just some constant, which in this case is C star over R squared. All right, so we can go further. Remember that the actual rate energy at some distance r, contained now within a cylinder of radius r, is going to be the integral from the inner conductor to wherever we are of the energy density times the volume element. So that's going to be the integral of C star over r squared, a to r, times 2 pi r dr times L. And lo and behold, this is again just going to be the integral. Let's see, we have C star times 2 pi times L, and that's all going to become C, let's say, double star. And then we're going to have an r over r squared and a dr, so we're left with dr over r. But brilliantly enough, the constant is, after all, constant, so I'm going to bring that outside, and I'll have some constant C double star, the integral from a to r of dr over r. And that's easy to integrate. That's going to be natural log, right? So we'll have C double star, natural log r evaluated from a to r, which is C double star, natural log r minus natural log a. And then the trick, of course, is that difference in natural logs is the log of the quotient. So we get C double star natural log r over a. Okay. But of course, the total energy inside the thing, which we might call U total, is of course just the energy contained in a cylinder of radius b. So it's going to be C star, C double star, natural log b over a. And therefore, the fraction we want, the fraction of total energy within our cylinder, is U of r over U total, which is C double star natural log r over a over C double star natural log b over a. And then this is where our cleverness pays off. We were able to ignore all of these constants because in the end they're going to cancel out. And so we have that the fraction is just the natural log of r, natural log of r over a over the natural log of b over a. It's really tempting that there's some like crazy maybe law of logs things that go on, but I can't see any way of combining those natural logs. The ratio of natural logs has no special property. Anyway, so then our original problem becomes, let's put it this way, find r such that f equals 0.27 when A equals 0.19 centimeters, and B equals 0.23 centimeters. I mean, I guess I could have written that originally. That was what we were saying. But now we have this fraction, so we could do it. There are two approaches. I'm going to do the quick and dirty one, and then I'll probably do the longer, more analytic one. But the quick and dirty one, of course, is to just graph it. In other words, graph this function, and then graph that value and see where they intersect. So here it is in Desmos. Here's our expression for the energy as a function of your radius, and it's some constant times that log. Down here, there's the constants defined to be 1. It doesn't really matter, as we know it's going to go away right here. And we say, well, here's our fraction, which is just the ratio of the stuff less than less than radius r over the stuff that's entirely in the in-between region of the capacitor. And here f naught is what fraction we want it to be. And here's a cute little Desmos trick, which I just learned actually right now as making this video, which is that we can actually find intersection values by actually just saying functions and making Desmos fit those functions, just like any other fit function. So I say take that the fraction at some value is the thing we want at that value, which is of course constant, and then plot that point. And we see what comes up is this, which is 0.200006. And our desired fraction of 0.27. So we find that the radius that we would want, after all is said and done, the radius that we want would be 0.20006 centimeters, which is probably, given that we only really had 2 digits for the other guys, is probably 0.20 centimeters, which makes this problem kind of ludicrous in that it's such a small fraction. If I want roughly a quarter of the energy, I have to be only a tiny bit of fraction over. I have no real sense for it, but there we go. The other, less quick, less dirty way of doing this is to solve it analytically, going back to the fact that our desired fraction is natural log r over a over natural log b over a. We can just exponentiate and get an analytic result. And so what we do, of course, is we just raise, I guess why don't we solve this over and say we have the fraction times the natural log b over a is the natural log r over a. And then we should exponentiate both sides. So e to this stuff is e to that stuff. I'll also do a casual flip then and say that e to the log r over a, that's just r over a. All right, and of course that's equal. And then here I'm going to rewrite things a little bit, and I'm going to write it, instead of what I have, e to the f log a b over a, I'm going to write that as e to the log b over a to the f. Because we know that e to the gh is e to the g to the h, or whatever. I'm saying that something kind of go off to the side here, that, for instance, 2 to the 2 times 3 is the same as 2 squared cubed. And so, right, because over here we have 2 to the 6th, which is 64. And over here we have 4 to the 3rd, which is, of course, also 64, in case you didn't believe me. Going back to what we had here, so we've swapped the order of the exponents, and now I have e to the log b over a, and that's going to be something kind of neat, because e to the log b over a is, of course, just b over a. Of course, it's still to the f power. So we have this, which means the analytic answer that we eventually wanted here was that. And I'm going to go back to the colors we've been using, the colors I used at the very start. So the thing that we want, which is r, is equal to, I'm going to cross multiply by a, and then I'm going to have a fraction to some power, and that fraction is going to have a on the bottom and b on the top, and then the fraction that I wanted, the fraction of the energy I wanted was f, and we'll put it there. We can put in the numbers that we were given, so 0.19 centimeters times let's see, the bottom here was also 0.19 centimeters, and the top was 0.23 centimeters, and the fraction we wanted was 0.27. And if you grind that out on a calculator, lo and behold, what you get is 0.2000058, which of course is the 0.20 to sig figs. The fact that we get 0.0058 and Desmos got 0.0006 is clearly a rounding issue, possibly just in the display, actually, not even in the calculation. So we have it analytically, and we have it graphically. The graphical way, as you can see, was faster, although not really that bad. I thought this was going to be a lot worse than it turns out. And I guess in the future, if you ever needed this, you could see, you could go in here and say that you have your functional form. So that's kind of neat. Also notice that if we wanted the fraction to be 0, which would be weird, we can see that we would get something to the 0 is 1, so the r would just be the inner radius a. That makes sense. And less weird is if we wanted all of the energy, the fraction would be 1, and so this would just be b over a. These would cancel, and we'd find that r would have to be the outer radius b, and that makes sense too. So that all works out.